So good day, morning or evening, whatever time. Okay, but no good night. Okay. Now let's talk about another beautiful arrangement called a transformer. That is the two types, step up or step down. And these transformers were proposed and made and installed etc. by Henry in United States of what is known today as United States of America. Okay. So at Princeton he produced transformers. Well, if there is a voltage which I can write V is equal to capital V root 2 sine of omega t, where this is the RMS value and this is the instantaneous value. Okay. And if following Joseph Henry, you can see that there is a core here. Okay, there is another core over here. Soft iron core is there, so that the flux linkage may be optimized. So in that case you can see that the primary and the secondary coils are wound on the same one over the other on the soft iron core. Alternately, what we can do, we have a soft iron core and the linkage is through this soft iron core, and one side I have the winding for the primary and the second side the winding for the secondary. Okay, so it's like that. The schematic diagram for that, the symbolic thing is something like this, where I have got these two lines, and these two lines speak of a soft iron core. Okay, which is missing over here, and here the core is air core. On the air you have one winding and then another winding. One is primary and the other is secondary. Which is down and which is up, it doesn't matter at all. Okay. So normally what we are going to talk about right now is the electricity which is available to us as supplies in our homes, which is 50 Hertz and 60 Hertz in the Americas. So they change. For example, in India we have a left-hand drive following British people, and in many a country it is right-hand drive. Okay, I'm sorry, we have a right-hand drive and they have a left-hand drive. It's just to for economic reasons, so that they don't have to pay royalty to the original designer. So that way, let's say that these wires which are wound in the primary and the secondary coils, they have an insulating character. They are insulated from each other, so if they are closed, then there is no contact between the adjacent layers. Well, they are insulating wires. They can be, if they are copper or anything there, then they are enameled or insulated. The wires are of low rate resistance per unit length, and they are wound as shown. These transformers with the soft iron core, they are called AF transformers. Okay, A stands for audio, F for frequency. Audio frequency 20 Hertz to 20,000 Hertz, so it is there. Okay, but at higher frequencies there is a problem with the cores, and therefore we go for air core windings. Okay. So we have to compromise on the resistance per unit length also. If we have to take thin wires, then the resistance will be more, etc. So one thing is pakka. One thing is essential, and that is that there should be a low resistance in the primary. And we consider that there is approximately 100%, which I take as 100%, flux linkage between the primary and the secondary. That means the same flux passes through the primary coils and secondary coils. Okay. Now if phi is that flux per turn in both primary and secondary due to current in primary at a given time t, and we say that the applied voltage is Vp, say. Okay. So what happens? This flux per unit turn, this induces a voltage in the secondary, which I can write as Es is equal to minus Ns d phi over dt. Okay, minus Ns over d phi over dt. So this one. Okay, the alternating flux which is happening there, it introduces a back EMF in the primary. It's very interesting. So that back EMF in the primary turns out to be equal to minus NP d phi over dt. So let's encircle both of them. But EP is equal to Vp, what has been applied to the primary. And if EP were not equal to Vp, the EMF to the voltage, terminal voltage, if it were not so, the primary current would be infinite, because the primary resistance has been taken as equal to approximately 0. Okay. If not infinite, then this is very hard. Okay. So after we talked about the primary, we'll talk about the secondary. If the secondary is kind of an open circuit, or the current taken from it is very small, okay, then we can write the approximation. Es is approximately 100% the value of Vs, where Vs is the voltage across the secondary S. Then I can write these two equations. Vs is equal to minus Ns d phi over dt, and Vp is equal to minus Np d phi over dt. So I divide this Vs by Vp, and this cancels out, and the minus signs go, and we get Vs upon Ns is equal to Vp upon Np. Now this is what has been obtained. Okay, we can also write this as capital Vs and capital Vp, because the RMS values, they also cater to it. And in doing so, we have taken three important approximations. First, that RP goes to 0, but IP is not too large. IP is not infinity. IP is not infinity. Okay. So this is one approximation, and the second approximation that we took was that the flux linkage is 100%. Flux naturally it is the same per unit turn of primary and secondary. So this is the beauty of the transformer theory, and also that IS is taken, the secondary current is taken as small. Okay. Now we can talk about the efficiency. Efficiency is the power output divided by the power input. Okay. And the power is given as I into V. So Is into Vs is equal to Ip into Vp. The two powers are equal. That is the efficiency. Output power divided by input power. Output power divided by input power is equal to 1. Okay. Similarly, we can write that Vs upon Vp is equal to, from this equation, Ip upon Is, which means that if we have a design so that the voltage goes up, volts up, current down. Okay? Volts down, current up. So here, how I define this, that Vs is equal to NVP. If n is greater than 1, then we have a step up system, and if n is smaller than, then this is a step down system. Okay. So if the voltage steps up, then the current comes down. Okay. If you have in mind that what, like transformers, we have amplifiers, but amplifiers, the function is different. The amplifiers, they amplify signal into a larger signal by taking voltage and converting that DC voltage into the desired AC voltage. Okay, that's the primary definition. So now I can write that Vs upon Ps is equal to Vs upon Vp is equal to Ns upon Np. Okay, here I have taken the RMS or effective values, and Is upon Ip is equal to Is upon Ip is equal to Np upon Ns. So in this case, the efficiency has been taken as 100%, which it cannot be. Why it cannot be? There are several reasons for that, and one of the reasons, some of the reasons are related to the magnetic energy associated with the systems. The others are related to the electrical resistance in the primary and also in the secondary. Okay. Moreover, there are eddy currents which will be there, okay, and other things. So I just enumerate for you the reasons why, even for the best of designs, the efficiency cannot be 100%, okay, or 1. Now, let me talk before I go to enumerate the various losses which are there in the transformers. I'll tell you something more. That is, it is due to the transformers that the electricity which is generated at far off places, by any means, chemical, carbon burning, fuel burning, gas burning, etc. That powerhouse is normally located away from, and sometimes several tens and hundreds of kilometers away from the place of consumption. So what we do is like this, that we produce the voltage at a low value, then we boost it up, we step it up so that the current becomes small. So I square R loss in the transmission, that becomes low. Okay. At the destination point, again that very high voltage, that could be 11,000 volts, that may be brought back to 440, and from 440, when it is to be supplied to the factories and houses, etc., then it is brought down to 220 volts here, and other places 110 volts, sometimes it is 240 volts, etc., etc. Various countries, they have various standards, but anyway, the power produced at long off power stations, that comes to our place through the use of this thing, transformers, and we cut on the losses of transmission, etc. And a very interesting thing I will tell you, that the transformer was designed and built up. Even there is a choke coil. If you are interested, you can just used to be used in bringing down the voltage in the case of these tube lights. So there we don't have two turns, we have a single turn, and that is used as choke. So choke means choking the current there, and that is called wattless current. So in all those cases, for the capacitor, for the inductor, those power factors being equal to 0, they are wattless currents. Currents are not equal to 0, the power is 0. Say they are called wattless currents. Okay, so that way in the final use of the transformer, I have to tell you very interesting thing, that the transformers were built and the transformers were used on the continent. When I say on the continent, that means in the eastern and western parts of Europe. They were not used where they were built. So the nation called United States did not use these transformers. So the story goes that when the son of the mayor of New York, where the cost of electricity was very high because it was associated with Edison company, Edison Electric Supply Company, and the cost was very high. Maybe let us say it is in Indian money it was say 10 rupees per unit, but in Italy and other parts of Europe that was about 3 to 4 rupees. And that boy was astonished, the son of the mayor of New York, who had visited there to learn culture and civilization which existed in Europe at that time, which was not there in the United States of America. They were supposed to be Durras at that time. Okay, Durra is the English Hindi word, and you can even search the meaning, it's available. Okay, rustics, that's what is said. I don't have anything to say about the Americans. They are great people, they are great nation, and all nations they want to go to USA these days, but so it was not used there. So there was a company in you must have heard about it. That company's name was Westinghouse Company, and this boy, he invited the Westinghouse Company to come to the shores of United States of America, and in big ships they shipped all their equipment, they shipped all their technicians, they shipped all their supervisors, everyone, and the Edison Electric Supply Company was out of job, and Westinghouse worked there because of the transformer which was basically built by Henry, and it was manufactured also over there, and on demand the transformers were sent to the continent. So now we'll take about and talk about the various losses. So the losses are of 4 kinds. The first one is flux leakage. This is because of windings that are there, sometimes the winding is not according to the proper ways. Improper windings are there, faulty windings are there, and in the windings there are some air gaps, and the air gaps are very funny, and particularly in the case of not only transformers but in particular for the choke coils. If you talk to the old generation who were using the tube lights with choke coils, they will tell you that yes, there has been a buzzing sound. And interestingly, if we have a 50 Hz supply, and then I have studied that buzzing sound with the help of a cathode ray oscilloscope and displayed that on the cathode ray oscilloscope and measured the time period, and I found that the frequency that is that comes to our ears, and that's very annoying, that frequency is actually 100 Hertz, simply because the sine square of omega t or cos square of omega t is converted into 1 minus 2 cos of omega t divided by 2, so that the frequency of the time dependent part becomes doubled. Okay, so flux leakage is one of the things which is associated with the winding flaws. Number 2 is winding resistance. Winding is done by means of wires, and all wires they have some resistance or in length associated with them. When we talk to technical people, technical hands, they call the winding resistance losses as copper losses. All other losses, so flux leakage is one, eddy or Foucault currents, because the variation is very short, 50 Hertz and more than that in the case of audio frequency systems, transformers that are there. Then of course, because of the quick rise and fall of currents in the core, metallic cores, iron cores, eddy or Foucault currents are there, and because of these currents there is I square or heating, etc. So that is for the audio frequencies. If you use the same core at the radio frequencies, everything system will get choked immediately, because the radio frequencies are very high and the rise and fall is very quick, and the eddies are immense nature, and nothing goes to the secondary. Then number 4, because of the rise and fall that takes place for the magnetic path, that is hysteresis, and hysteresis finds its remedy in search for low hysteresis loss cores. Okay, so these things are called iron losses, particularly these two, iron losses, and the winding resistance that is called copper losses, but these are the terms used by the technical staff. Okay, these kind of losses are also present in the windings of motors, etc. That if it is sometimes the motor windings are burnt out, you take it to a mechanic who will be able to fix that, but he will talk about the iron losses, the copper losses, and these days they are using aluminium wires, so they can call it aluminium losses. So it has been a pleasure to talk about this alternating currents, which has come to an end, and we are going to delve into what are known as the electromagnetic waves, where we will talk about at least two grades. Another two grades. Faraday the Great, and then we will have James Clerk Maxwell, who unified everything, electricity with magnetism, with Maxwell's equations, and then the genius of an experimental physicist in Heinrich Hertz, who died young at the age of 37. He was a great man who produced and show the Maxwell's equations, and he established, therefore, that there has been a controversy that light or electromagnetic radiations, basically they are waves. Okay, so Newton called them corpuscles, Huygens called them waves. It was established by other means, but it was confirmed by this, but it was short-lived, and then came the Planck's constant and Planck's quantum, and then h nu minus h nu naught of Einstein, which established that waves are particles. And it took about another 16-17 years for de Broglie to say if waves are particles, well, particles are also waves. So the duality was there, established by de Broglie, a French young man of 21 who is the youngest ever to receive the Nobel Prize in Physics. Of course, Malala has been the youngest so far to receive a Peace Prize. Thank you very much.